Okay, so we're following on from the talk 2 weeks ago, and we're in the process of constructing part of the ingredients that we need to construct a strong deformation retract between a cut and something that has the composition of two morphisms in LG as a direct summand. So the definitions we need to work from here. So we're working in the context of a potential K, also V in this polynomial ring. The idea is that this is sitting in the middle of two other potentials, these morphisms we're constructing the cut of. And we've got a sequence of partial derivatives of this potential. And then we've got the causal complex of this sequence, right? And we're denoting the module KT like so. Where these DTI are formal generators. Okay, and we've also got the Jacobi ring, which is the polynomial ring KY, modulo the ideal generator by the elements of that sequence. And our aim is a strong deformation retract between the Jacobi ring as a complex concentrated in degree 0 and the causal complex. Okay, I think that's about all we have, and then I'll remind you of a couple of definitions from the previous talk as well. So onto the second board, we have the definition of say R K algebra, and I guess no. So just ignore that. So given T as above, we define a system of T derivatives as maps del T1 through del Tn from Ky to Ky as K-linear maps, satisfying the following properties. So for F in Ky, F can be written as in the following way, as the sum of as a polynomial, I guess, in the Ti's, where these are used belong to the common kernel of these maps. Reminder that this thing is sorry, this should be to the n here. This thing is T1 to the U1 all the way through to Tn to the Un. Okay, so that's our first condition on this set of maps. The second one is that it differentiates the powers of T like so. Where EI is a vector with, it's the ith basis vector, I guess, in n to the n. And for F in KT, which is the K algebra generated by one T1 through to Tn, and R in this kernel that del Ti of Rf is R times del Ti of F. Okay, and then given such a system, we define a connection, which is a map on the causal complex, which is given as follows. So if we evaluate it at this element of the causal complex, then it is given as so. Okay, for all f in for all polynomials f in the ring Ky. Okay, and then I'll just recap the statements of the lemmas that we are going to use, that we proved last time, that we're going to use going forward. So I guess, oh, I better move over. Oops. Number one, I guess, we proved that the connection squared is equal to 0. Lemma 2, we showed that if Q is an element of K, I should say this is a field. So if K is a field of characteristic 0, then dk nabla, the image of this thing, is just this ideal, or the image of kt under this thing is this ideal. Oh, okay. The next thing is that dk nabla is a morphism not just of modules, but of complexes. So it commutes with the differential of the causal complex. And then finally, again, if Q is, so if K is a field of characteristic 0, then this commutator is invertible away from degree 0. And so invertible as a map of modules. Okay, were there any questions about that before we move on? Okay, so we'll continue on the fourth board. So from now on, we're going to suppose that Q is containing K. So K is a field of characteristic 0, and that T is a causal regular sequence. I guess we already know that, right? Because V is a potential. Okay, so we define a map H, which will end up being the homotopy in our strong deformation retract as this thing. Right? In all degrees where KT is non-zero. And H is just zero elsewhere. And notice that this makes sense by, I think it was, which lemma was it? Lemma 4 on the previous board, because this thing is a degree +1 map, right? So this inverse exists in all degrees that we need it to in order to define H. Okay. Okay, so now for another result. So the degree 0 part of the map 1 minus dkh factors through the Jacobi ring. Okay. Okay, so to show that, we need to show that some f in this ideal is 0. So we know by a lemma that I wrote up on the previous board that dk nabla of kt is this ideal. So we can take some g in kt such that dk of nabla of g is equal to f. Okay. And now we just compute, right? So we have 1 minus dk of h of f. Well, that is just dk nabla of g minus dk dk nabla inverse nabla dk nabla of g. Okay. From here, we can write this as, so we still keep this term out the front. And we can rewrite this as, this term stays the same as well. And we can rewrite the next thing as the commutator dk nabla minus dk nabla of g. Okay, now this term goes away because nabla squared is 0. And so this and this obviously cancel out to be the identity. And then we are left with dk nabla of g minus dk nabla of g. And we end up with 0, right? So that proves that. Okay, so let's go back over to board number 1. Oops. Cool. Okay, so now we'll define a map pi from kt to I guess the Jacobi ring concentrated in degree. Maybe I should write this properly as a map of complexes. So we'll let that be the quotient map. In degree 0. And then, of course, it is just the 0 map everywhere else. And then by the previous lemma, we have a map sigma. I'll call it sigma naught from JV to the 0 part of KT, such that 1 minus dk H0 is sigma pi, or pi sigma, I guess. Then and then I guess we'll extend this to a chain map. Okay. And now we're ready to prove that these maps form a strong deformation retract, which is what we were going for. So we'll do that on starting, I guess I'll write the proposition on this board. So proposition, the maps pi, sigma, and h form a strong deformation retract. So we have dB, 0, okay, over K, I should say. All right, all these maps are K-linear. Okay, so what do we need to show? So let's take a look at the second board. We need to show the following. So first of all, we need to show that pi sigma is equal to 1. Second of all, we need to show that h dk plus, so h is a homotopy, so dk h is equal to 1 minus sigma pi, right? So h is a homotopy between sigma pi and 1. And then so this is enough to show that this thing is a deformation retract. And then finally, we need to show that the deformation retract is strong, right? So that h squared is 0, that pi h is 0, and that h sigma is 0. Okay. So for 1, away from degree 0, there's nothing to prove. So in degree 0, we can represent any element of JV by something that looks like that, where F is in KY. And we can also assume that F lives in the kernel of all of the del TIs, right? Okay. Well, in that case, we just compute. So we compute pi sigma pi of F. Well, that is the same as pi of F minus dk h of F. Right. So I guess that's probably an extra step there, I guess. Minus dk. Now this thing is 0 by our choice of h. By our choice of f. So this comes out as pi of f. So this proves 1. Okay. Therefore 2. In degree 0, we have that 1 minus sigma pi 0 is equal to dk h0, which is enough because if we write out h0 dk, sorry, oops, give us a sec. Oh, this is terrible. well, this thing is equal to 0, right? Because that's where the causal complex ends. Okay, so there's nothing really to prove there. Away from degree 0, so let p be greater than 0, then we need to show, well, let's compute this. So we'll compute the commutator. Okay, so that thing is writing in the definition of H. Okay. And then, so we now use that this thing is a morphism of complexes, right? So we can pull in the second part, we can pull this thing past the differential there. Right. And this only works because p is greater than 0. If p was 0 here, then the differential we're trying to write down would not exist. Sorry, this inverse here that we're trying to write down wouldn't exist. And then from there, we just note that, well, this thing is just dk nabla inverse times dk nabla commutator. And so that is just equal to the identity. And then away from degree 0, pi and sigma are just the 0 map. So this shows 2. Okay. So just 3 left to go. And we'll take a look at, I probably want to leave that board up. So we'll go to board 5. Sorry, board 4. So now we just have 3 to go. Okay. So we'll first show that h squared is 0. So h squared, well, that is dk nabla inverse nabla dk. Right. And what we're going to do is we're going to show that this thing equals 0. Okay, so we know, well, let's write that out. So if we compute like this, so we have dk of nabla, well, that is nabla dk nabla plus nabla squared dk. Well, we know from previous lemma that that's equal to 0. So that is equal to this thing. Which gives us dk nabla nabla. Okay. And then we can rearrange this to get nabla is equal to dk nabla dk nabla inverse. And then we can just multiply on the right, or I guess compose on the right by nabla again to get 0 is equal to nabla. What does this show? What I claim is this shows that dk nabla inverse nabla is equal to 0, which doesn't seem to make sense to me. Oh, sorry. No. Yeah. Okay. So, well, I guess directly this shows that we have dk nabla nabla dk nabla inverse nabla equal to 0, right? But in this degree is greater than 0. Well, unless all the other maps are 0. So this thing is invertible. So we find hence h squared is equal to 0. Right? Okay. Okay. Next, well, the next thing to show is that pi h is equal to 0.
Wait, can I check that logic? So you're saying kind of multiply both sides on the left by dk nabla inverse twice or something to get h squared?
Sorry, no, that wasn't very clear. So multiply on the right by nabla.
Yeah.
To obtain this line.
Yeah.
And then this thing is invertible. Or this thing is 0.
I don't know what you mean. So how are you deducing h squared equals 0? Is it because you get from that equation the right hand side is h squared somehow? Or you
Oh, sorry, no. So this
equation?
implies because this is invertible, this implies that the rest of it must be equal to 0.
Mm-hmm. I think the inverse is outside the bracket. Yeah.
Yeah.
You wrote
yeah,
nabla inverse. Yeah.
Yep. And that is part of our formula for h.
Okay. Yep.
At the top here. Yep. Cool. For pi h equals 0, well, if we have so.
Sorry. Now I want to check that logic. So.
Yep.
That is what Dan said, right? So you start off with 0.
Sorry, I just realized that now.
This thing.
Yeah.
Yeah, and I compose on the left by dk nabla inverse twice, and you get 0 equals h squared. That's what you do. Okay.
Yep.
Cool.
Yeah. Sorry about that confusion. Okay. All good if I continue? Okay. Okay, so we have that HP, so in these degrees, for, well, if P, we have this to be equal to 0, since if P is not 0, then HP is equal to 0, pi P is equal to 0. And if P is equal to 0, then H of minus 1 is equal to the 0 map. So this thing is always equal to 0. And then finally, we can show the last step. So let's take a look. I guess we'll go back to, I'll do it at the bottom of board number 3. And then finally, we want to show that H sigma is equal to 0. Okay, so away from degree 0, again, this is clear. And then in degree, yeah, okay, and then in degree 0 we have h of sigma pi. Well, this is just h minus h dk h. And then this is dk inverse never. Okay. Then we can rewrite this like so. So we have okay. And then I guess the thing to note here is that, well, this term cancels with, I guess, the factor we get from here, right? And then we just showed that nabla followed by the inverse of this commutator followed by nabla, that this thing is equal to 0 as well. So we end up again with 0 in this case. And that completes our proof for showing that we have a strong deformation retract. And I guess that's all I've really got to say today. I don't really want to get stuck into what we're going to talk about next. So yeah, I'll say if anyone has any questions, then feel free to ask them now. Otherwise we might leave it here for now.
Okay, so I didn't quite follow that last line. How did the first term cancel? How did the first term cancel?
Okay, yeah, maybe I'll write this out a bit more. I'll just redo this thing on the let's say on the first board again, and I'll actually write out all the steps this time. Okay, so we're trying to show we've got h. So this thing that is equal to h minus h of dk h. Then writing in the definition for h. Okay. Oh, sorry, this should be a nabla here.
Mm-hmm.
Okay, and then if we expand the brackets, we keep this term. Oh, I've missed a whole thing at the end here, haven't I? So this should be not just nabla, this should be dk nabla inverse, right? Coming from this h.
Yeah, that's just the definition of H.
Yeah.
Right.
I missed that before.
Yeah,
Okay. And then, well, this cancels with this to give us dk nabla inverse nabla. And then we have, in the last term, we have minus dk nabla inverse, and then nabla dk. Oh, sorry, this is. Sorry, this is the wrong way around, right? Because we want to replace dk nabla by. Sorry, nabla dk by dk nabla. Okay. Then this term cancels with this term, and then when we were showing that h squared was equal to 0, we showed that this thing is equal to 0. So we end up with 0 at the end. Does that make sense?
Cool. Yep, that makes sense. Cool.
Okay.
Nice. Good job.
Thanks, Rohan.
Yeah.
One question, Rohan.
Yep.
A question. Is there a way to derive the formula for H instead of just having it posed as by definition? Is there, or at least some? Do you have an idea how to interpret this formula from an intuitive point of view?
I don't really have much intuition, I guess. No, I don't have a lot of intuition for this formula. I mean,
not this one. I'm speaking about the definition of H, which is
yeah. So H
kind of,
equal to this thing.
Yes. Yeah. Exactly.
Yeah. I mean, no, I don't know a good way of saying this is why H should be what it is. Sorry. Yeah. I don't know if anyone else does.
It all works too well.
Yeah.
Once we got this.
Yeah, I mean that inverse of the commutator is maybe less mysterious than it looks. If you look at what it does on an actual form. So if you take a product of these generators of the exterior algebra underlying the causal complex and apply this thing to it, it effectively just puts in scalar factors that sort of divide by if you take a form that looks like some polynomial of degree d times a form of degree e, so that is like ddt1 time wedge ... ddte, so e wedge products, then it will put a scalar factor 1 divided by d plus e, and that's all. Modulo, okay, it's not quite true. There's some, that's modulo multiplicate terms that are divisible by t and so on. So, but roughly speaking, that's what it does. So in some sense, you can just, to a first approximation, think that H is just nabla. And then this is very similar to the de Rham complex, if you're familiar with that. So you sort of, in one direction, you're multiplying by the TIs, and in the other direction, you're differentiating with respect to the TIs. That's what nabla is. So then the fact that H is a homotopy comes down essentially to the fact that, there's some commutation relation between multiplication by TI and differentiation with respect to TI.
TI.
So that's kind of the underlying idea. I mean, you can come up with this. I did come up with this formula just by trying to find a homotopy by hand, and then you kind of notice that something, you end up with this. So I suppose it's maybe the way to really understand what it means is to study the example where the TIs are just the variables and think carefully about, like, try and construct by hand a strong deformation retract on the causal complex of just the variables in a polynomial ring. And you'll kind of see this emerge out of that if you try and do it by hand.
Okay. Thank you.
Cool.
Great. All right.
Okay.
Look forward to the next installment in 2 weeks.
Yeah, sounds good.
Thank you, Rohan.
Thanks, Rohan. See ya.
Thanks. See ya.
Cheers.